So they're going to go look at the solids, and they're going to make a comparison between the two of us. And essentially, we're going to have them determine for us the following question when it comes to flow through a vessel. We want to know, are the rules for a solid and a fluid the same when flowing through a vessel? And this is in order to make sure they can make progress on that, we did some of the preliminary work, and Mike's going to mention what you're looking at here.
So we ran the flow depth experiment using 4 different orifices, 6 millimeters, 8 millimeters, 10 millimeters, and 12. We ran these 4 to determine whether or not the flow would be steady state, because with the fluid it changes with the height. So we plotted our data of mass over time, and we got a straight line telling us that it is indeed steady state. We didn't start collecting data till after a few seconds. And so as you can see from these straight lines, we are at steady state. And we took the slope of these lines to get the actual mass flow rate. And here we plotted our mass flow rate for each orifice against the orifice diameter. And we fit a power function to that. And after doing some reading, we found there's actually a correlation called Beverly correlation. And as you can see at the bottom, this equation, the C is normally about 0.58. You take the bulk density, gravity, and the D0 is the diameter size. The K is about 1.5, and the D is actually the particle diameter, the particle size. And so that's a corrected value which we did. You can't see that in the table there. So we got our experimental value was x to the 2.5, which is the same as the Beverly correlation 5/2.
So you're plotting this versus the excluded orifice size.
Yes.
Where I follow that, they're not plotting. So for example, if they got 6, here they're plotting 1.5 down from that, or something like that. Okay.
And at this point, after we get this far, moving forward, we're going to depart from the juniors, and we're actually going to design the geometry for a bin. In order to do that, we're going to take materials properties using a rotary shear tester. We're going to determine the yield stress of the powder and the friction of the powder on the wall of the vessel, and then we're going to use those properties to design the geometry of a hopper. Questions?
Can you show your Excel plots again, 4 plots?
These 4?
Yeah. So you notice that they don't go through 0, right?
Yes. Yeah, we're taking our y-intercept to be the mass at times 0. So we started our data collection after some time, and so our time 0 is not actually time 0. And so our y-intercept should be the approximate mass at the time we started taking data.
Is it?
The y-intercept should be what?
I mean, is that what you started, the weight of the empty bowl, or is that, or are these times from when you started the experiment? Or
It was allowed to run for a couple.
I'm trying to understand where 0 is for the solids and for the
Zero is its valve open, but we don't start taking weights until a certain time, and usually about then.
These are real time.
Yes.
So it's good they're all positive.
Yes.
Because but there should be in principle 0. Yes?
If we
If it
had
started, yes.
yes, if we had started taking data.
So I guess my point to you is you should think about what that means in terms of unsteady. And if you come to me, I'll find you a reference for that. Not maybe necessarily something that you need.
And what's the vertical coordinate?
Good point.
The vertical coordinate?
Yeah. Oh, it says mass over here. Mass of the stuff that got,
Yeah, we may
collected?
some things off because of cramming.
yeah, but the mass is what? The mass that has gone through?
Yeah, the mass that we've collected
mass
whole underneath.
Okay.